Okay, so hello everybody, and thanks for joining this webinar. So we have the pleasure to have Jérémy Dudouet, who is a researcher at IP2I Lyon, and we'll be presenting some practical tools for structure and gamma-ray spectroscopy, which are TkN and Cubix. So Jérémy, whenever you want.
Thank you, Louis, and thank you everyone to be here and to be so many. I'm very pleased to see so many people. So as Louis said, I will present two tools that we have developed. So the first one, which is a toolkit for nuclei, known as TkN, that I have developed with Diego. And the second one, which is more dedicated to gamma ray spectroscopy, which is named Cubix. So I will start with a bit of history, or of my history with these tools. And all of this started for me actually at the beginning of my postdoc in Lyon in 2015 when I joined the Agata collaboration, and I took part at this time to an fission experiment with Agata and Vamos. And I had hundreds of different spectra, gamma ray spectra to handle. It was my first steps with gamma ray spectroscopy, and I started at this time to think about how I could automatically analyze all the spectra. And this is how the first version of Cubix appeared. So at this time, it was a graphical interface based made with roots and integrated into the GammaWare package, which is a package for gamma ray spectroscopy. And it was using also the Caliveda library for different aspects, for handling nuclei or some graphical tools. At this time, it was only a tool for my personal analysis because it was reading my own trees with hard-coded the branch name I was using. So it was not a community tool at this time, but it was already supporting peak fitting, gamma-gamma analysis. But a few years later, I started to work on a new version of Cubix, where the idea was to be able to share Cubix version, which is no more dedicated to my personal analysis, but as a community software to make analysis of gamma spectra from whatever experiment. The only prerequisite was to have spectra in root format. So at this time, it was still integrated in the GammaWare package, but this is the first version which was not that was a thing to anybody in nuclear physics for gamma ray spectroscopy. Another story started also at this time in around 2019, 2020. This is how the TkN, so toolkit for nuclei, has been linked. And actually, all of this started by Dominique Durand that requested to Adrien Mata if it was possible to integrate a nuclear model code named Sleepy in Geant4. And as I was the one that developed this model Sleepy, Adrien asked me if how it can be done, and if I was agreed to help him to integrate Sleepy in Geant4. And I started to discuss with Diego how we can do it. And after a few weeks of discussion, it diverged completely. And in the end, we decided to make a standalone project that was a library dedicated to nuclear data to extract published data and having all of this in the standalone library, C++ library. And in the end, Sleepy was never made in Geant4. So all of this for nothing for the Geant4 side. And so 2 years after, the first release of TkN appears. Thanks to the COVID time, we had plenty of free time to work on it, Diego and me. And after 2 years more, in 2024, I published the first Cubix version powered by TkN. So now I will give more details on all of this. I will start by presenting the TkN library, and then I will show how to use Cubix. So to start with TkN, I show here the concept. So what I'm calling the physics, nuclear physics playground. We love nuclear physics because of its richness. We have hundreds of elements, thousands of nuclei, hundreds of thousands of states and decay and millions of properties like energies, lifetime, Q values, etc. So we have a very vast amount of published nuclear data. And I'm sure you all know how it can be complicated to extract all of this to make systematics or nuclear models. And so this is what here I'm calling the nuclear physicist nightmare. I'm sure you all have tried at least once to extract data from ENSDF. Oh, I see there's plenty of people waiting. Or to extract data from NUDAT and from the IEA API. And we have plenty of different formats to handle, like web page, PDF decoding, some legacy database formats like ENSDF with this 80 character format. And it can be very complicated to have this in a standardized way. And that was the idea of making TkN, because most nuclear physicists have their own custom scripts, macros, or utilities to extract some subsets of base data. So this leads to duplicated efforts, fragile workflows, and it's limiting in terms of reproducibility. How is built the TkN project? You can see this on a three-step project. The first one, so as I showed before, is the official sources. So in TkN, we are extracting data from ENSDF, Xundul, I will see more about this later, from NUDAT, from the IEA API, we obtain data for X-rays and for chemical elements. And all of this is automatically parsed and used to fill SQLite database, which is the TkN database. So all the first step is only for developers. The users don't need to see it at all and start with the database. So in this database, we'll have access to elements, isotopes, level, and decays. And then we provide a C++ library, what we call the TkN interface, to have all the tools to play with this database without having to know how to handle a SQLite database. With this interface, you can make some nuclear physics analysis, simulations, semi-systematic plots, what you want. So what you can access in TkN, so it's just few examples, not an exhaustive list, but for the elements, you can have like atomic masses, radius, X-ray energies. For the isotopes, you can have abundances, decay mode, charge radius, deformation, mass excess, Q values, and all what can be extracted with the mass excess, like the neutron or proton separation energies. You can have some fission yields. For the nuclear levels, you can have the energy, lifetime, spin and parity, the feedings, and for the decay, you can have the energies, the initial and final states, intensities, the transition probabilities, the multipolarity, etc. So now I will just say a few words about how is built the database, even if it's not really necessary for you to understand it, just to give some indications. So we have the SQLite database. We have 5 tables: elements, isotopes, level, decay, and datasets, which are linked with foreign keys. Typically, each isotope is linked to an element, each level is linked to an isotope and a dataset, and each decay is linked to 2 levels, the original and the level from and level 2. And all of this helps to have a very fast read of the database, even when you want to make like a coincidence analysis. Typically on modern computers, you can read the full database in few seconds. So now how you can use TkN. So there is typically three steps, three ways to use TkN. The first one is command line tools. So using the few executables we are giving with the project. Then you can work in the root environment. We'll see with the TkN root, you can work with TkN classes in the root interpreter. And then, if you want to go to more complete analysis, you have the C++ library of TkN with a full integration in your codes. So now we will go one by one, and I have tried to make some integrated videos to show how you can deal with this. And we'll start with the TkN config, which is level 0 of TkN using. And this is the elementary program to know how the program has been installed on your computer, what is the version you are using. Here, for example, 2.4. You can ask what is the database you are using to know at which date it has been released. And you can also have the Git commits that you are using. So typically, if you are contacting us for any problem, this is the three information we will ask you. Then you can use the TkN print program, which is a very simple program to print standard information of nuclei. So for all of these programs, you can start just with the name of the program and -- help. It will give you all the different options, arguments, etc. And then you can print your favorite nucleus. So here I'm printing the properties of T132, and it will print the really basic information. But if you want more, you can just use the long option. And here you will see we will have access to like fission yields, to Q reactions, Q values, X-ray information, binding energy, all of this. Then you can print then you can print the level informations. So you will just use the -- levels option, and you will see here all the different levels with the known properties like spin and parities, lifetimes. You can do the same for the decays. So just -- decay, and you will see all the decays that are known for this nucleus. And you have the final possibilities to write at the same time level and decays. And for each level, you will have then all the decay information of the decays decaying from this level. I think it's all for this video. And before moving to the next, I wanted to give you an example of what you can obtain where when you are using the classical web API of ENSDF and Xundul. So I'm sure you all already have done it plenty of time, but when you want to have some information on nuclear structure for one nucleus, you go on the ENSDF website, you enter your favorite nucleus, and then you can have access to many datasets. So what is called a dataset is a way to produce this nucleus. It can be like a beta decay, it can be a Culex, it can be a fission, and you have for each dataset the different level and decays that has been associated to this dataset. When you want to see this, you have two possibilities. You can see it in PDF or in raw format. I'm sure you never asked the raw format because you will have this kind of thing, which is not user-friendly at all. But this is typically what we are using to parse the information in TkN. But then what you are doing in general is to look at the PDF and find the information you want in the PDF. If you go below, you will have all the datasets which are associated to Xundul. I don't know if the difference is very clear for everybody, so I will just mention it. The ENSDF evaluators are doing a very hard job. For each publication, they have to evaluate all the measured published data and to make the evaluation and build it in databases. So once the data have been evaluated, it will be stored in the ENSDF database, but all the data that has been published but still not evaluated by the evaluators are the called Xundul databases. You can see that in general, the last released for ENSDF are quite old because this is a very complicated and long work. So if you want to have the very new publication, even if it's not evaluated, you need to go in the Xundul, and you can see here you have like dataset released in 2026. Okay, so this is just to explain you that when you are using TkN, you will have exactly the same information. namely. Still with your TkN print, you can now ask to plot the available datasets for your nucleus. And you will see here for this TIN132 that you have first the ENSDF, so the evaluated datasets, and then the non-evaluated datasets which are available. For each dataset, you have a PID and you have the release dates, which is exactly the same that we have seen in the web browser. For each dataset, you have the possibility to print the comments which are coming with the published dataset. And this can be useful to have information like which detectors have been used to collect this data, what kind of measure that has been done, how have been estimated uncertainties, etc. And yes, I have not shown something which is important. In the dataset, there is always at the beginning a dataset which is called adopted level and gammas. And this dataset is actually a merge of all the evaluated datasets. So the default dataset when you are asking a nucleus will always be the adopted level and gammas, which is containing all the evaluated datasets, not the Xuntul one. So then you have the possibility to request a specific dataset. For example, here I will ask to show the levels for the dataset with this PID. And the list you will see is no more the same than before because you are here requesting this dataset. Okay, here I'm just showing two different datasets to see that we have differences in what is shown. The first one was, I don't remember, this one is Culex, I think. And you can print the comments also for the level and decays. So typically here you will have some comments for the levels saying from which work the BE2 has been evaluated, or you can have some information of how the level has been measured or something like this. Okay, I think that's all for TkN print. The next step is the interactive use of TkN inside root. And for this, we are, if you have compiled TkN with root, you have an executable which is called TkN root. And that will start a root session with TkN loaded inside. You will directly see which version you are using and which database you are using, and then you can directly call the C++ API, but in root, and to make the same kind of prints that what we have done with TkN print. But here you will directly manipulate the C++ objects. You can list the properties of your nucleus, but you can also obtain the pointer on, for example, here, the level scheme, and then you can play with your level scheme. So you can print it as we have done with TkN print to show the datasets, to show the level, to show the decays. You can also select a dataset directly from the interface, but you can also recover the different levels. So here I will directly obtain the vector of levels, which are in shared pointers. And I can ask to just print the first level of my list, which is the ground state, or the second one. You can, with this pointer, directly obtain the energy. So typically, this is how you will use it then in your C++ codes. You can also extract transitions. So here, I'm showing a way to extract a transition from its string. Typically, I will ask the first 2+ to first 0+ transition in a string like this, and it will directly give me the pointer to this gamma ray. If I'm printing the gamma ray, I will have all the information, but you can also extract all the information you want. So if you are in the interpreter, if you press tab, you will have the completion. You can see that you can obtain the transition probability, relative intensities, multipolarity, etc. You can see also that in some cases, you will see, for example, get transition probability, get transprob, but also get transprob measure. Actually, the first one will just return the float value, The second one will return an object, TkN C++ object called a TK measure that will allow you to access the value, but also the uncertainty, some information on is that the data coming from simulation or systematic or from measure. And it will also give you the units, and then you have the possibility to play with the TkN unit manager that I will not present here, but you can see you can have more information on the web documentation for this. So here you can see I obtained the BE2. You can print it, but you can also just request the value. Like this. So here you have the double associated. You can have the error. So in your C++ code, this is how you will handle this kind of information. Okay, so that's all for the TkN root. Now the next step is to use TkN in your macros. So here I'm not speaking about a full C++ development, but just a simple like a root macro. And here I'm just showing a very simple example where I am making a loop on all the nuclei which are known by TkN, asking to have just the even one. And I will, for each nucleus, retrieve the level scheme and extract the 2 plus to 0 plus and 4 plus to 2 plus transitions. I will extract the quadruple deformation of the ground state, and I will extract the BE2 of the 2 plus to 0 plus transition. So you see that with like 10 lines of codes, I have able to extract information from levels, decays, ground states for all the nuclei. Then you execute it. And in a few seconds and 10 lines of codes, you are able to have a full systematic on the full nuclear chart. If you try to do this without TkN, just by parsing by yourself all the files needed to do this, it will be much more complicated work. So now a few words about documentation and resources. So if you go on the TkN webpage, which is tkn.in2p3.fr, you will have all the information you need. So on the first page, you will find the publication and the different presentation we have done and available. All the information about the licenses and how to make references in your work when you are using TkN. And you will have so two contact of the developers, Diego and myself. And there is also a user channels on the Rocket Chat of in2p3, but which is also available to anyone that has EduGain access, and which is the place to ask any question about the software. Then you can click on download and install. And you just have to follow what is written here. The dependencies are very small, and you just need to have git, cmake, C++17. And if you want to link with root larger than 620, but you can also use TkN without root. It's not mandatory. So then you just have to make these different steps to extract the source code from the Git, make the cmake command, the installation, and setting up the environment. And if all is set as it should, you can extract the root version and see that you can, for example, here apply the TkN root and see the database you are using. Then you have examples to integrate TkN in your developments. So in the website, there is a dedicated page for this. The first thing you can do is, like we have seen, like a simple macro. You can just compile in TkN root your macro and execute it. Then you have the possibility to build your own TkN executable. We give an example which is called TkN exec.cpp. And here, if you want to compile it, you will need to give the good link to the TkN libraries. And for this, you just have to use this command with the TkN config that is automatically giving the good flags to make the compilation. The next step, the next step is if you want to integrate TkN in a cmake project. For this, we are providing also a simple example on GitLab. You can extract this cmake example, and you will see how you can and what are the lines you need to put in your cmake file to link as it should the TkN program. The final possibility is if you want to include TkN as a Git submodule. And here also, we are providing in the Git repository of TkN an example, and you can just download this example to see how you can see here TkN is linked as a submodule. And in the email list, you can see what are the lines you need to put to include correctly TkN as a submodule. For the documentation, there is here, you can go, first you are in the data sources, you have all the sources we are using to extract the TkN database for isotopes, for level decays, etc. Here you have all the programs we are providing, the one we have seen before. The release note, which is quite important. Each time you want to see there is a new version, you can see all the new tools or utilities that has been added or the bugs that have been corrected. And then you have this TkN user guide where you have all the information on how to use the different elements, nuclei, levels, decay, the TkN data manager, the measure, TkN measure, the TkN units, and how to play with multi-threads with TkN. And finally, there is a deoxygen API that will allow you, as you do it quite usually, I guess, for root, for example, to go for any class of TkN. You will have the full documentation on of this class, and then all the different methods with the commands. And you can see, for example, this method get energy with the parameters, how you need to use it, etc. And then you have some examples which are giving. So with a list of examples we have developed, you can click on it. You will see how to execute it. You will see the code and the result you are supposed to obtain. And the final one is a gallery where we have put some images performed with TkN, and you can just click on the one you want, and you will have access to how it has been realized with the full code and explanations. Last thing I wanted to say about TkN is that this is an open development. So there is a GitLab repository. You can access it directly like this. You can see that we have a CI/CD to be sure that for each new push, we are making some tests to be sure it's compiled, it's doing what it should. And we are very few users, so anyone is welcome if you want to contribute to help to add any new features. You are very welcome to contribute to the TkN project. So up to here, we have seen all the TkN parts, so all the nuclear data parts. And now I will speak about Cubix, which is a tool for, as I said, gamma ray spectroscopy to make spectra display, to make gates, peak fitting, and calibrations. But now both are integrated workflows, and so you can also in Cubix have the tools of TkN like peak identification, nuclear data navigation, or making gamma search with coincidence search, etc. So I have not started this project starting by zero. There is already a lot of very powerful tools that are existing since a very long time, namely Radware, Gasware, or GammaWare. But for the first two, for example, Radware and Gasware are written in old code style, like Gasware is mainly Fortran, Radware is C, and the last release are from 6 or 9 years, so they are no more maintained. For Radware, the website is actually no more accessible. And that's why I wanted to work on this new project, because they were not allowing to open root format, which is what I was always using. And that's why I started to integrate in GammaWare, that was already in root and C++, some utilities from Radware or from Gasware that were also already existing in GammaWare. I just used what was existing to then provide new tools. So that's how Cubix has been developed. It's full C++, root native, cross-platform, and open source. So what you can do with Cubix, so here also I will show some videos because I don't want it to take the risk to make like an online crash test. So when you start Cubix, you will see that in background, it will load the TkN database. It's very fast, and it will open the Cubix window. In the Cubix window, you have on the right part, the standard global Canva part to make the plots. On the left, you have a browser, a bit like the root browser, and you have a menu bar with different options. So here you can play with canvases. Here it's for some view, the different tools available, and some options. So then you can just navigate in your browser, open a root file, and any root object will be able to be plotted. So here, for example, you can see all the spectra that are in a subfolder. And if you double click, you will just print, display your spectrum. And then you have utilities to play with axes, zoom, with plenty of different keyboard hotkeys to play with your spectra. The next step I wanted to show here how you can use Cubix for detector characterization and play with workspaces. So the first one is energy calibration. So if you have like here a raw spectra for here it's a germanium spectra of europium, so a source data. You can just open it, and in the input data, you can if you click on show available sources, you will see all the different sources that are already accessible in Cubix, but you still have the possibility to create your own source if you want, or if you want to mix sources. So you just have then in input data to write the name of the source you are using, and it will display all the theoretical peaks that it will try to have. You can just zoom on one peak to have a very approximative idea of the resolution of your spectrum. You click on calibrate, and you will directly have all the peaks that are fitted with a plot of the calibration and the residuals for all your peaks. So once you have done this, you can just click on apply, and you will have a calibrated spectrum, so in energy. So here I'm showing how you can save a calibration in a workspace. So typically a workspace will be dedicated to like an experiment and an array of a detector that you will use many times in your analysis. So here I'm just creating a new workspace which is called demo, and I will store the calibration in this workspace. The next step you can do is making efficiency curve for your gamma spectra. So it's the same. You will go in tools, efficiency, and you will also provide the source you are looking at. You will define the resolution. Here we are in energy, so I reduce the resolution to have something which is working. You click on build efficiency curve, and you will directly have your efficiency curve, which is plotted. Then you will just click on fit. So it's using exactly the same functions than in Radware. I have just copied the way it's done in Radware. And if you click on fit, you will have the fit efficiency curve with the error bands that are displayed. And here also, you can just save the efficiency curve in your workspace. So I will add it to the demo workspace. And that's all. Another thing that you can do is to make an estimation of your resolution, of the resolution of your detector. And here, it will be the same. You go in the calibration tool. And instead of doing calibration, you make FWHM calib. And here, what it will produce is a plot with the resolution of your detector as a function of the energy. Here also, the function is taken from Radware. And you will have the possibility to store this curve in your workspace. And we will see after why it's important to have these information. Okay, and so now for the workspace, you just have to go in the workspace manager. And for example, you will see that here I have 4 different workspaces which are defined, one for Gamma Sphere, one the demo we just have created, etc. And for each workspace, you have access to the different curves you have built. So here I'm selecting the active workspace. So now the active workspace is demo, and I can plot the different curves that are stored in my workspace. Last thing I wanted to show for the detector characterization is the possibility to make batch calibrations. So if you have a matrix for which in which you have the energy as a function of the segment, not the segment, the detector ID, sorry. You can, for example, here, well, this is an Agata matrix. I have the segment ID of Agata as a function of the energy. And I will just make a projection with this as this is the cobalt source. I'm just checking the approximated raw resolution to adapt my automatic fit procedure. And I will, because this is cobalt, remove the offset from the calibration. No offset. And here you calibrate. And this will directly produce a plot with the resolution of all your detectors. And if you want to extract the calibration parameters, for example, to feel like how to define, if you have calibration files and you want to put the parameters for all your IDs, you can just reduce the verbosity level, reduce the step, and it will produce, you will have printed for each ID the different calibration values. Okay, that's all I wanted to show for the detector and characterization. And the next step is peak fitting. So here I'm still with my European source. And the first thing you can do if you go in the 1D player utility is to make a peak search. This is a very standard peak search. I will say very roughly what are the energy of the peaks that are detected. It can be very useful in a very first approximation. But then if you want to make dedicated fits, you can just zoom on your fit and click on the set on the peak fit utility. And here what you just have to do is to pick on the background region and the peak or peaks if you want to fit many peaks. The order is not important. It will just take the first and last one as background and the other one as peaks. Here you have click on fit, and you can see that actually the fit is not good. If you look in your terminal, you will see that the resolution is fixed at 2 because here 2 is the minimum value that is authorizing the resolution. So you just have, for example, in this case, to change the range for your resolution, you reduce the fit, and it's much better. You can see here in the terminal that you will have the amplitude, mean value and amplitude, the Gaussian, because we are giving the possibility to make a fit of a Gaussian plus tails. And if you have no tails, the Gauss and resolution real will be the same. But if you have tails, Gauss is just giving the resolution of the purely Gaussian part, and the FWHM real will give the real resolution with the tails. Then you have the tails value, the area, and if you have a workspace which is activated, you will have the efficiency corrected area. Yes, and here, if you have a workspace which is defined, you see that for the resolution, you can click from workspace. What it will do actually here is that it will use the resolution curve you have defined for your detector to fix this value in the field. Because if you know perfectly your detector, actually this resolution is no more supposed to be a free parameter. So you can either fix it or just allowing 1 or 2 as you want sigma using the uncertainty of your resolution fit. For the background, you can see that you have the possibility of playing with different type of background. Here, you can have just a flat one, polynomial one, exponential, or the one we are using in general in gamma ray spectroscopy, which is the step background to take into account the Compton ages. Okay. The next one is how you can use fit with more than one peak fit. So you just have to select a region with a double peak. Like before, you click on set, you make your background, you click on your 2 peaks, the background, fit, up, and you will have the fit, and in the terminal and in the interface, you will see the different properties of each peak that has been fitted. Okay. The next one is using Cubix for coincidence with 2D spectra. So you can plot, if you have a gamma-gamma matrix, you can plot it like this. You can then play as you want with the display of 2D. But if you want to make gamma-gamma coincidences, there is a dedicated utility, and you just have to make init gamma-gamma from the matrix or directly from the browser. And it will open the gamma-gamma utility, where you have on the top the projection, 1D projection, and below you will have the gates that you are applying. Here it's a symmetric matrix, but you can ask if you want to gate on X or on Y. So here I will show how to put a gate. So you click on gate, you just have to make a drag and drop on your pick, the same for the background, and you can put as many background as you want. When you are happy with this, you click on project, and below you will obtain the projection. Okay. You can see here, this is here a rotational band in zirconium. The gate is on the 2+, and then you don't see anymore the 2+, but you perfectly see the 4+ and 6+ in coincidence. You can move in a dynamic mode that is allowing you to have the dynamic projection. It can be useful in some cases to check if your peak is real or not, or if you want to see on the left or right side of the peak if the projection is the same. You can sum your gates. That will be a do or typically of your gate. And here you will see that now we are seeing the 2+ and 4+ because we are summing a gate on the 2 and a gate on the 4. And you can here use your workspace by clicking on use the FWHM. And if you do this, you don't have anymore to define the width of your gate. It will directly apply your width as a function of the resolution of your detector. Here I have just I click on the histogram and I made add to the stored list, and this is here a list of spectra you can store to then either display them or store them in root file. Okay. Another thing you can do is to open the gamma-gamma utility using the called Radware utility. Here I have just implemented what is done exactly in Radware. So in Radware, you are not defining background gates, but there is a background estimation that is done automatically and used for the subtraction. So here you just have when you want to do your projections, you just have to define the gate. So here you click on gate, you put your gate, no background to define, and you project. In general, this is a bit over subtracting it's over subtracting. So you can play with both ways of doing the gate, which have both interest and disadvantages. And here I will just I have added both in my stored list, so you can play with the spectra to compare them. You can open the editor to change the color if you want to show the different spectra. Okay. I think there is still one thing I wanted to show is that you can play with the number of projections. So here you can increase the number of projections. For the display, it can be useful. And typically, what I will do is to put one gate on the first pad. I will show another gate on the second pad, etc. And then you can, with the crosshair, compare the energies for different gates. Okay, I will try to go fast because I'm already 45 minutes, but then you have the possibility to play with cubes. I have not defined my own cube format for the moment, so all is done using the Radware format. So you have a cube reader. You can read already prepared Radware cubes, so I'm using exactly the same way to make the gates. So here, for example, I'm putting one gate on one axis, the second gate, and here we are no more doing OR, but AND, so we are using with 3D matrices. You can do the projections. You have an utility, which is a cube builder, which allow you from a root file, a root T3, to create a cube in the Radware format and then to play with this cube in Cubix. So you just have to fill this configuration file, you execute it, it's very fast, it will create the cube. And then if you open it, you can directly, here I have built a cube for my zirconium 100 spectrum we have seen before. And you can, for example, here I will put a gate on the 2+ and 4+, and in principle, we should only see then the 6+. Okay. All I wanted to say for this. And finally, we go in what you can do with Cubix and TkN. So the first tool is the nuclear chart player. So if you go in Tools and Nuclear Chart, you can browse all the nuclear charts and display the different nuclear data available. So here you can show, for example, the TK modes. You have the B2, you have the isomer lifetimes. And then you can select your preferred nucleus. So for example, here I think I put carbon 12. It will make a zoom. You can have some basic information for the ground state, but you can also display the level information or the gamma ray. And you can also select the dataset. So here we are using by default the adopted level and gammas, but you can ask to plot the datasets for different way of producing this nucleus. Okay, the next one is the gamma search. So if I come back to my spectra we have seen before, let's assume that I have no idea which spectrum I am looking at. I can just start with a quick peak search, and I will ask to my gamma search to tell me which nucleus are containing these transitions. I just have to write for 1, 2, or 3 transitions and putting a width for the search. And here I clicking on start, it will say that I have 800 nuclei that have been analyzed, and all this list contain these 3 transitions, these 2 transitions. Then I can ask to have them in coincidence. And here the list is much smaller, and it tells me that the more favored nucleus is zirconium 100. And the nuclei are sorted by probability. This means that it's doing the intensities and the branching ratio between the different transitions. And if I have a probability of 1, means that I have the 2 transitions that are a branching ratio of 100% from one to the other. And now the gamma search is telling me that, okay, this is much likely 100 zirconium. I can just open then the ENSDF player, which can be very useful. When you have your spectrum, you go in ENSDF player, you write the nucleus you think it is or you want to show, and it will print directly on your spectra all the transitions that are known. Here there is plenty because this is adopted level and gammas with also all what is coming with beta decay, etc. But if I'm selecting a fission dataset, there is much smaller number of transitions. I can just ask the ERAST transitions, and you can see that indeed my spectrum is well corresponding to the zirconium 100. Okay, so quickly for the documentation part, you can also go on the Cubix webpage, so cubix.in2p3.fr. You can, on the webpage, you will have information on the how to reference Cubix if you are using it. So there is a Zenodo repository that you can cite. There is a newsletter. You can register if you want to have information when there is new release. And there is also a hotline. If you want to ask any question, you can just write a mail to this hotline. And in general, I will try to answer quite quickly. For the installation, as for TkN, you have all the information for the dependencies and how to install the software. You have 2 ways to install it. Either you can build directly TkN with Cubix, which is option 1, or you have the possibility, if you already have TkN installed on your computer, to link Cubix with your TkN installation to avoid having 2 times TkN installed on your computer. Okay, and finally, so as for TkN, you have the release note. Each time there is a new release, I'm trying to write all what has been done in this release. And then you have the user guides with all the different information for the graphical interface, all the keyboard shortcuts, the workspace manager, etc. There is much more than what I have presented here because I have not the time to show everything. But here you can see the shortcuts. You can see all the background player, what you can do with background subtraction, angular correlation, if you want to fit angular correlation, and doing event mixing studies with 1D or 2D mixing. And I think that's all. I forgot just to show also that as for TkN, there is a GitLab page, and for the moment I am the only member, but anyone is much more than welcome to come and contribute to add any features in Cubix. So to finish, for the future developments, we have few ideas in mind for TkN. We would like to develop a Python interface for data science like AI studies and Jupyter workflows. We would like to add particle decays. For the moment, we only have gamma decays, but we would like to add alpha, beta decays, etc. And we start to think to work on a TkN reaction, which is an extension of TkN, but to have cross sections of reactions, yields, etc. For the Cubix part, there is few things that I'm working on for the moment. There is a new format, which is chunknd, which is think to be a new multidimensional data format for modern computers to have a n-dimensional matrices. I am working on a level scheme generator powered by TkN and to make automatic level scheme generation. And I would like to add some standalone analysis tools, like giving example on how you can use the Cubix calibration tools, but not using the GUI, just using scripts if you want to include it in your calibration workflows. But here also, any suggestions, features, bug reports are much than welcome. And yeah, you can, if you want, you are welcome to help us to develop these tools. Thank you, and sorry for the delay.